Um, I guess I'm gonna try to give some kind of like motivation / overview of what's to come, and this is absolutely not at all well planned. So apologies ahead of time to everyone. And yeah, and then the other thing I wanted to say is please do interrupt and ask questions and point out things that interest you or don't interest you, or whatever comes to your mind. So we're talking here about chromatic homotopy theory. That today that's a huge thing, like a huge field encompassing all kinds of stuff. So where does that story start is basically the motivation for basically anything in homotopy theory is that there are homotopy groups of spheres. So these are the stable homotopy groups of spheres, or so this is a colimit or K of the n plus k homotopy group of the K sphere, and for short, we write just pi star of S naught. So basically, the way homotopy theory seems to be working since back in the 30s, when these homotopy groups were introduced, is you're trying to compute the homotopy groups of, say, spheres or other things, and you find that it's really hard. So then some theory gets developed to help you with that. And maybe the theory, this inspires some theory, and then the theory gives you some kind of technology, techniques to figure out something to compute, and then you get something, and then you notice something about this, and this sort of the circle keeps going, and then lots of times sort of things come in from other parts as well. So the circle sort of grows and gets more and more complicated. One of the first calculations was that let's say that pi n of Sn is the group of integer sort of given by the degree of a map. So you have two spheres, and if you have a continuous map of the same dimension, right? So if you have a continuous map between them, it sort of you can find a regular point, and then you count how many points are in its inverse image, and you get a number, and that number is going to be your degree, except you need to count something more to know whether it's plus or minus that number. And in fact, then one of the hopes in the early days of homotopy theory was that all the other homotopy groups of spheres are going to be zero. And that turned out not to be true, and has kept us in this business for almost 100 years. There's still a lot to do. It is true that if we have some, pi m for S, and this is 0 if m is less than n. But then the story of the degree, where we look at the pre-image of a regular value, gets works out in higher dimensions as well. So we could also try to compute pi n plus k Sn that way. But so the first ways of doing this were geometric, and lead to something that's called framed cobordism. So that's like Pontryagin, Tom, such people from back in the day. So when we look at the stable ring, the theorem then becomes that the homotopy groups of spheres is actually the groups of framed cobordism, whatever that is. The point is that there's some manifolds in there. There's a lot of geometry. It's hands-on in a certain way. However, this approach also led to some wrong calculations. So it's kind of hard to keep track as this codimension grows. Right. One of the reasons that this is so difficult is that, maybe we should. Okay, so yeah, so we have the integers. We have 0, then the integers, and then what happens after that is everything is torsion. So so this is actually was I guess due to Sayre. So maybe I should have written here, this is sort of the early works of Pontryagin, Tom, maybe Hurevich. Then what Sayre proved using his spectral sequence is that actually, if we look at, so this is here, actually turns out is maybe part here is like Freudenthal. There's the Freudenthal suspension theorem that's sort of telling us that these groups stabilize for a fixed n as k grows. So this thing here is also pi 0 of S naught. Okay, so so pi n of S naught is torsion. It's a finitely generated torsion Euclidean group for n greater than 0. So basically, yeah.
Just a comment on Zoom. You can write a little bit bigger because the video is not so clear.
Got it. Okay, I will do that. Okay, so pi n is torsion. So basically, it's going to be hard, like, finding some, 2 torsion is very close to being 0. And, it's really easy to make mistakes, like the famous sort of Kerr invariant is coming out of some mistake of that sort, where like 2 torsion, turns out, whether something is like Z-mod 2 or 0, geometrically, it's hard to detect such things. And then, so this happened in, like, this is from 1953. The other thing that we have about these homotopy groups of spheres is that they're not just groups, that actually this pi star of S naught is a ring. So this is also it's a graded commutative ring. And the way we sort of multiply maps is basically by composition. Okay, so the other bad news about this ring is what Nishida proved back in 1973, I believe, when the paper was published, is that this ring, so any element in this ring that's not, let's say, any x in pi n of S naught and is greater than 0 is actually nilpotent. Sorry, I forgot to write larger. So, you know, okay, well, right, like then you could say, well, maybe this ring is mostly 0, but it is absolutely not. So, you know, I guess maybe that question still remains, you know, like, okay, well, people figured out pi 1 is Zmod 2, but maybe after pi, I don't know, 7 or something, there isn't anything more, and that's not the case. And maybe the first sort of non-trivial family was in this sort of J of X papers. There's a construction of an infinite sort of non-trivial family of elements, all of them torsion, all of them nilpotent, but still sort of going to infinitely high dimension. So in particular, I mean, this has a lot of stuff in here, but in particular, there are elements, non-trivial elements in arbitrarily high dimension. For any, right? Like, it doesn't stop. So this is not a finitely generated ring. So so how do we understand this, right? So that's the main question. So everything here is nilpotent, and maybe the titles of, you know, at least like the name of a book that you're you're going to be trying to read is nilpotence and periodicity. And look, there's no periodicity, so what do we do? So making sense of that, the first steps of this sort of chromatic business are probably somehow this Adams's J of X papers contained that, though there were things that preceded that as well that got him to think about that. So right, so yeah, I don't know. So again, this is not very well organized. I'm not sure what comes first or how to give a linear presentation here. But so one of the important things that go in the theory here, right, like, okay, so what is happening? So we started with these homotopy groups of spheres. You could just define them because you can define homotopy classes of maps between topological spaces. And you just do that, and then you study some sort of geometry of manifolds and play with that. But things get out of hand. And so one of the sort of first things that you need in terms of theory is the category of spectra. So as spectra are things that basically every field of mathematics has its own notion of what a spectrum is. It's a sort of most favorite math word, I guess. So so there's two things maybe to say real quick about spectra. one is that what it does is it categorifies this notion of homotopy groups. So where do these things live? What's a homotopy group, and so on. And then the other thing that it does somehow at the same time is that, okay, we're looking at homotopy groups. People were playing with homology at the time. But what it does, it puts together other things there as well, like, K-theory and complex cobordism and framed cobordism. All of these things get to be living in the same world. So you have generalized cohomology theory, co-homology, homology, all on an equal footing in the same world, where you get to work with them at the same time. And so, for example, you have things like K-theory living here, which is for a generalized cohomology theory, which you could define by vector bundles and so on and so forth. But then all of a sudden, you could do things like, suppose I have a map from some sphere to another sphere, then I could look at what this map is in K-theory. So we could either look at K-homology or K-cohomology. Anyway, so we could look at, say, the K-homology of F and ask, what does that look like? And this is what Adams was doing, and in defining the E invariant of a map and so on. Okay. So some spectra that are going to play important roles in this whole chromatic world are, okay, so first of all, the sphere had, all of these spheres together. S naught, when I write S naught, I don't mean usually the space of 2 points, but the sphere spectrum. So then there is the, say, integer ordinary homology, or maybe mod P ordinary homology. But then the extraordinary ones are things like K, complex K theory, maybe KU. Let's write that. MU is going to be a crucial player, complex cobordism. So as a cohomology theory, what this does is on nice enough, small enough spaces, it assigns to it some kind of equivalence class of fibrations over that space that have as fibers certain types of manifolds up to cobordism. And so again, that's like a really geometric thing, but this it's just crazy. It has too many I don't know, universal properties and it has to do with a lot of stuff. And then from there are these for each prime, there is a BP that is that splits off of MU. So this is a Brown-Peterson spectrum. That's what BP stands for. And then from that, maybe you build other things, like then for each P and each N greater than or equal to well, if you want 0 and infinity can be included as well, there are these higher K theories, so Morava K theories spectrum.
You couldn't even conclude what spectrum would we call K infinity?
HFP. So K0 would be rational homology, and K infinity would be that. Anyway. The homotopy groups of this are sort of FP, and then you join a variable in dimension that goes with n, or maybe in dimension 2, but with certain properties. And so that's an invertible variable in a certain degree. And so if that degree is infinite, that it just doesn't exist. And if the degree is 0, you basically joined P and inverted it. So it's a convention more than anything else. Okay, so right. Maybe I should have kept this, but anyway, so then if all of these things are P torsion and nilpotent, what can we even do with them? So so suppose we have this sort of a map from some sphere to another one, so an element in pi m of S naught, and suppose it is like, let's say P times it is 0, right? So that means I can look at multiplication by P map there, and I know this composite is going to be 0. And then, okay, so what does that tell me? Well, now this is where these categorical properties of spectra are important. So the homotopy category of spectra, that, you know, nice triangulated category, we can take a fiber here. So it's more, it has, you know, it's more than that, but still. Anyway, so the co-fiber of this map here, so we mod out by P on the sphere, we get something that's called the Moore spectrum. So then we can take the fiber is a desuspension of this thing. And by somehow categorical mumbo jumbo, having this composite be 0 means that we can factor through here. So we get F tilde that is now a homotopy class in the homotopy of this Moore spectrum. And then you could ask things like, okay, what can I say about this map? And the things that Adam started doing over there is like, okay, well, now what are some maps on the sphere that are sort of like P torsion, or maybe like some power of P torsion? I have something like that. Now, can I actually, so can we extend this F tilde to SM mod P? So instead of it being a map from SM to here, what can we write it as a map? So then we would get, so if yes, we get a map from SM, let's say +1 mod P, or I'll write it as suspension M +1. So we get some kind of map. It's a self map up to this shift. It's a self map of the Moore spectrum. And what Adams did, among other things, is studied certain maps that come from this image of J, come from linear isometries or things like that in yeah, so give the automorphisms of spheres that way, and show that all of those can be extended to maps like this. And not just that, so there are these special maps that when we see them in K-theory, so K-theory has this nice property that it's a periodic theory, and these maps here, we see that they're not nilpotent in K-theory because of this period, the periodicity generator sees them, and so we know that they couldn't have been nilpotent there. So there's a special choice of such maps, which are not nilpotent in the sense that I could, like, I could iterate this and keep changing the suspension as needed. So, and then keep iterating and never get something that's null. So, which are periodic. Never null after iteration. Because they can be detected in K-theory.
You're saying these are maps between more spectrum?
Yeah. This is not exactly the way it's presented in Adams's GFX papers, but that's one of the outcomes from there. Yeah.
So the maps are periodic, not just in K-theory, right?
Well, in K-theory, they're periodic because we know what periodicity means, and we know that the maps cannot be null because they are never zero in K-theory, right? So the maps are non-nilpotent more generally. I'm not sure if the word periodic would have a sense there, but that's the periodicity. Yeah. And then somehow the cool thing is that you get to keep going. And this is where that sort of loop of theory, technology, and calculation sort of gets a huge input on the theory and technology side. There are lots of questions here. So one is like, okay, well, this is a little bit moving away from the point of like computing homotopy groups of spheres only. But mostly that's because it's also really hard still to do that. Right, so what this is saying is like, oh, I started with a map from this to the sphere. And then from it, sort of, we're asking if we can build a map on the Moore spectrum. And that sort of, the map on the spheres is still nilpotent, just it has to be. But this is just telling me that, maybe there's a whole family of maps that you could, and maybe sometimes you get to reverse the direction. Like you have a self map of this Moore spectrum, then there's this sort of standard, what used to be standard back in the 60s, I guess, and 70s is like you do things with cells, you pinch the top cell and, whatever like fun words that people said about that stuff. And you collapse some cells and do this to the cell and that, and you get a map from, from a sphere to a sphere. And it's absolutely not at all clear even today whether, say, all maps of spheres can be done, like obtained this way. I don't actually know if there's updates to that statement. Okay. Yes.
So if you take a map F that has, let's say, order K, right, so that's finite order, but its induced map on the Moore spectra does not have finite order, then what can you say about the induced map of F, like K times F, which is null on spheres, but it seems like the K times of the induced map of F is not.
Yeah. So what you get is things like these like E invariants. So you get so depending on when and like how many times you get to do this, you can see maybe where. It's like one thing I'm sorry, my mind is going this way. I'm not. You will see where you might be able to detect that map in filtration of some spectral sequence, like in this particular case, in the K-based Adams-Novikov spectral sequence. So this is arguably very technical, but I think that that's exactly what it's telling you. It's like you have some map, and then this so being yeah, depending on like which homology theory you see it in, like maybe you see it in K theory, maybe or you don't see it in like some, you know, yeah. Anyway, so I think how many times you get to do this procedure is how many times when you lift something to somewhere you get something null, but then eventually something is not null. That's a procedure that tells you how high you are in a certain filtration. That is also used in building some of these spectral sequences. Maybe there's more geometric way of thinking about this, but I don't know. To me, that's the most natural thing in the world. All right. So okay. So the thing is right. So suppose we have something that's sort of like this Moore spectrum or like the sphere. So the general world. So say we have spectra, and inside of there's things called finite spectra that I guess these days it's maybe written like that, but you know, in the Hopkins-Smith paper, the homotopy category of this thing is called C0, and maybe P local. Okay. So one thing that we said, sorry, I said early on was that the homotopy groups of higher homotopy groups of spheres are all torsion stably, and so that torsion can be analyzed one prime at a time. So it's a abelian group. You say, well, okay, I'm going to look at the 2 torsion and 3 torsion and 5 torsion and so on. And the same kind of procedure can be done on the level of the category of spectra, so that, you know, you don't worry about the extension problems. There's never going to be a map from Z-mod 2 to Z-mod 7 that's not 0. So the same sort of things happen in spectra. Anyway, so here we have P local finite spectra. And then there are several notions of what it means to be nilpotent, as you know, in the world of like maps here. But so the kind that we were discussing here is, suppose we have a map from some finite spectrum F to itself, F in C0, Then the Hopkins-Smith, Devenetz-Hopkins-Smith nilpotence theorem is that we can know if this map is nilpotent by checking not just its K-theory, but the MU homology. So the theorem is that MU detects nilpotence, that is, so if in MU homology F is 0, then the map F itself is nilpotent in that if we keep iterating, eventually it will become 0. So, I mean, this is actually pretty. I mean, it's kind of striking, and it's also a really hard theorem.
Do we have a concept that say MU detects nilpotent, so it's F is nilpotent, is it going to be 0 and it's small?
It is at least going to be nilpotent. I don't know if it has to be literally 0. I think if we want to write down an if and only if statement, we definitely need to write. Oh well, okay. We can definitely do that if we write nilpotent. But I don't know if it has to be 0 on the notes. Yeah. Well, F doesn't have to be the sphere, right?
Right.
Yeah. So, I mean, for the sphere, we know that there's not going to be many non-nilpotent elements. I guess Nishida already told us that. And then the problem is, like, F could have MU homology that looks like, something in the like Vn and then Vn mod some power, and then you would need to iterate a few times, possibly. Okay. So actually, instead of MU, so an alternative version of this theorem that maybe is not too, like, once you have this, then getting the other one is not too complicated, is that you could check that Kn star of F is 0 for n between 0 and infinity inclusive, and now here it's going to be literally 0 or not. Like, nilpotent here is not going to make sense because these are fields. Yeah. So these theorems came about from as I guess Devenetz, Hopkins, and Smith were working through Ravenel's crazy paper. It's probably one of the best papers in homotopy theory, localization with respect to certain periodic homology theories, or some combination of words like that. So Ravenel wrote this paper. So that's kind of just dreams up some stuff like, wouldn't it be great if things worked out like this and like that? And it turns out, yeah, it would, and they do. And the only thing that's left from there that's complete unknown still is the so-called telescope conjecture, but I won't go into that now. But before that paper could come about, there's this notion of like a huge further input into the theory, and that's Bousfield's localization. So the idea is quite simple. However, making it work is not, because there's some crazy set theoretic issues when you try to localize. But thankfully, Bousfield did that for us. So what this is, maybe if you are, I don't know, if you've studied homological algebra a lot, or things along those lines, these notions of localization come about, like, localizing a category, modding out by Serre subcategories and things along those lines. So this is an analog of that in the world of spectra. So so this is, so suppose E is any spectrum or any generalized cohomology theory. Then basically we can split up our category of spectra into things that E sees and things that E doesn't see. So X is E acyclic if the E homology of X is 0. So those are the things that E does not see. And then Y is E local if there's no maps from any acyclic into Y. If for any X, which is E acyclic, maps from X to Y, so this is homotopy classes of maps, is 0. And then an E localization, so localization with respect to E is a functor that gives you, so for starting with any spectrum, it gives you sort of a universal E local thing that maps to. So and E localization is a functor L sub E with a natural transformation from the identity. And then we need to describe its universal properties, that it's the terminal E equivalence or something like that. Okay, so so such that for any X, a spectrum, X to LE of X is an E equivalence, and for if X to Y is an E equivalence, then this factors so we have a factorization like that. Yeah.
does the equivalence mean in E homology?
Yes, thank you. E equivalence means is an equivalence in after smashing with E. Yeah.
And this thing, this is like activity elo spectra, the like subcategory, right?
Yes. So then the E, so basically then every spectrum X has a map like this to an E local. Then if we take the fiber, maybe we can write that CE of X, then this fiber is E acyclic. And then what happens is that if we have a map to Z, and the Z is any E local spectrum, then we get to factor that way. So so what Ravenel did is take this and say, well, here's that list of nice, interesting spectra, you know, MU, Morava K theories, BPs, truncated BPs, a whole range of this kind of spectra that were supposed to detect certain types of periodicity, and puts in localization with respect to those spectra as an object of study, and relates that to the behavior of elements in the homotopy groups of spheres as were detected in, say, the Adams-Novikov spectral sequence. So somehow preceding all of this that I didn't even mention is the work of Miller, Ravenel, and Wilson, where they did this Adams thing of detecting, you know, V1 periodicity. So that's the periodicity that's detected by K theory through the eyes of MU or BP as seen in a spectral sequence. And that was sort of all computational. And then basically Ravenel hints with these conjectures, and then Devnitz, Hopkins, and Smith prove it that this is just a reflection of the structure of the stable homotopy theory, like the category itself. So maybe I'll just make that statement then. One of the statements that's kind of crucial, let's erase here the bigger part of the board. And this is proved in the Hopkins-Smith, so the nilpotence 2 paper, although it's all dependent on the nilpotence 1 paper, Devnitz, Hopkins-Smith. So the theorem is that, well, maybe before the theorem, the setup that includes actually several theorems that come before this. It's okay, we had this C0 that now maybe disappeared. So C0 is supposed to be finite P local spectra. So this includes things like the sphere mod P, so the Moore spectrum. Then, you know, this mod P Moore spectrum had a certain map that we could see is non-trivial in K theory. It had periodic behavior. What if we mod it out by that? That's another spectrum that we get, and it lives in this world. And so things that are obtained as by, you know, co-fiber sequences and so on, starting from the spheres infinitely many steps. So that's finite spectra. So inside of here, there are these subcategories, C1, C2, and so on, and up to C infinity. And so Cn here contains the K, what is it, n-1 acyclic subcategory spectrum. So P local finite spectra, which are acyclic with respect to K theory of one thing less, one height less. So first of all, there are these containments here, and that's a non-trivial theorem. To know that, for example, having the, K, let's say, K0, so if that was rational homology, if the rational homology is 0, then the first K theory of that would be 0. So, I mean, and then it keeps going that way. So, oh, by the way, sorry, this is completely, I missed, maybe I implied it, but like I didn't state it here. The big theorem due to Bousfield is that these localizations exist, right? So, localizing with respect to somehow like a set of maps is not a big deal, but this is not a set, and that's the issue. Anyway, so going back to these, so we're looking at the acyclics, and so there are these inclusions. It turns out these are proper inclusions. That's also a very much non-trivial theorem. Constructing things that are in one of these but not in the other is highly non-trivial matter. And then the theorem is that actually, say C inside of the C0 is what's called a thick subcategory. So what that means, it is closed under weak equivalences, cofibrations, and retracts. Then C has to be one of these. And this is a really powerful theorem, and like the ways that it can be used is say like, okay, well, I want to prove something is all of finite spectra. Like some category that has, say, properties A, B, and C. And so if those properties A, B, and C tell me, like make this into a thick subcategory, by some abstract nonsense. So if I know it's a thick subcategory, then all I need to do is prove the spheres in it, and that I'm done. Or maybe it's not C0, maybe it's C7, and then all I need to do is prove that it's a thick subcategory and it contains one what's called type N, type 7 complex. So you'll see more of that as you read through this stuff. The reason why Bousfield localization plays a role in, first of all, coming up with some setup like this, and secondly, proving it. And other things that like sort of, okay, so what does one do with something like this? So structurally, then, okay, you get this on finite spectra, but then there's other things that this allows us to do. Like, you could sort of understand the sphere itself by its localizations, and that sort of puts sort of merges together the approaches of like, okay, how do we tell the difference between these maps that we could see by K theory but not by, say, K2 or by K7 or something, right? So there are associated, like basically it's for each of these numbers, there are also, not because, so these are Kn acyclic, there's also like, therefore there's Kn local things. All right, basically times, okay, there's no, why is there no bells here? I was waiting for the bell. All right. So basically, I guess I'll just end here by saying that this is telling us also then how we can assemble our problem by basically these localizations are saying, well, the things I could see by K theory are the things that I could see by K1 localization. So while the sphere may not have any periodic elements, the K1 local sphere does. And so you keep going with that K2 local, K3 local, and then there's also questions of patching things back together, which are crazy hard, but that's the idea, that sort of the localization puts makes this precise in a way that was not possible without it somehow. Cool.
I have a couple of questions. One is, all the categories that have been on the board today, are these homotopy categories or infinity categories or model categories?
Your choice.
So this statement is true even not on the homotopy category level?
This statement, the notion of, so I think if you try to define what's a fixed subcategory in, say, infinity categories, you'd have to define it's a full subcategory generated by those objects that satisfy. So it's going to be a homotopy category statement ultimately anyway, but yeah.
I know that, like, I know there's some work of Balmer on that, right? Where because there's the fixed subcategories and there's the localized subcategories, and I guess there's the result that these are the same thing here, but like I know.
Oh, that's a very different. Okay, that's the different direction, right? So this is now we're in finite spectra, and so there the fixed subcategories and localizing subcategories are the same thing because we are dealing with just finite things. So there's also a question of localizing subcategory more generally. In finite spectra, the thick and the local are going to be the same. In all spectra, they're not, even in the homotopy category of spectra, because not everything is finitely. So then there's this, that's the telescope conjecture basically in this point of view. But most of what I'm aware of in Balmer's work, he's working with triangulated categories, period. Right?
He's working with the triangulated categories, but all of what he does pretty much is extended to symmetric monodal infinity categories, which is why I brought it up.
Yeah.
Because he talks about, you say the telescope conjecture is true or false for this category.
Right. Yeah, but the idea is just this, that sort of the notion is on the level of homotopy categories, then you look at the full, whatever, full subcategory spanned by those objects. There's more.
Maybe I'll just ask if anyone else has any questions. Yeah. All right, so maybe we should wrap up because it's at the hour. Let's thank our speaker again.